Today we are going to discuss a VBT, and the full form is valence bond theory. Basically, valence bond theory was first suggested by the two scientists that were Hitler and London. These two were the scientists that suggested this theory, that is a valence bond theory. Talking about the main features of VBT. First and the main feature is half-filled or half-filled, we can say unpaired orbitals with the same axis come close to each other and this whole activity we can say that is called overlapping. So what was the main feature of VBT? That half-filled unpaired orbital with the same axis come close to each other, that is known as overlapping, we know, and that theory was given by the Hitler and London. What was the feature? That the half-filled means the unpaired orbital with the same axis come close to each other, and this activity is known as overlap. There are two types of overlapping: sigma overlapping and pi overlapping. Sigma overlapping means it is more overlapped and it is a strong bond, and it is a weak bond, it is less overlapped because of the sigma bond between them. For example, like we are having one orbital px, second px. Now these are the electrons. When they come close to each other, means when they attract each other, they will overlap. So it will overlap and it will combine. These px and px will combine, so one electron will be clockwise and second electron will be anti-clockwise. So that is known as overlapping when the two unpaired orbitals mix together, we can say not mix but come close together or overlap, that is known as overlapping. Basically, VBT theory can apply on the molecule that is diatomic. Diatomic means it can be a homomolecule or it can be a heteromolecule. Homomolecule like O2, N2, F2, these all are homomolecule, mean the same molecule, like OO, nitrogen and nitrogen, these are homomolecule. And heteromolecule like HCl, hydrogen, bromide. So these are heteromolecules, mean the different molecules. So basically the VBT theory can apply on the molecule that are diatomic, means homo as well as hetero. For example, let's take O2. Now oxygen has 8 electrons, 2 in first shell and 6 in the last shell or the outer shell. If we talk about the electronic configuration, so it is 1s2, 2s2, 2px, 2py and 2pz. 2 and 2, 4 electrons are covered, so here 1, second, third and fourth. So that is actually the electronic configuration of oxygen. Now if we talk about like shells, the orbitals, that is the nucleus. First is a K shell, and in K shell there will be only a 2 electron, that will be 1s2. There will be only 2 electron, and then the second shell, that is L, that is a K, and that is L. Now here it will be 2s2, 2px, 2py, 2pz. Means here are different orbitals in the present in the same orbit. This electron comes in K shell and these electrons come in L shell. Now the different orbitals in a same orbit having a little difference, means energy difference is too little because these are in a same orbit, so they are having a like little energy difference, we can say. But if we talk about K and L, that is in another orbit and that is in another orbit. These orbitals are in L orbit and this orbital is in K shell. So there will be highly energy difference between these orbital K and L. But if we talk about the same orbit L, there are the different orbitals. They are having, means these orbitals are different but present in a same orbit, L orbit. So they will be having a little energy difference. But if we compare K and L shell, this orbital is in K shell and this orbitals are in L shell. So these are having a highly energy difference. Now as we know that the shells, the orbitals that are in different shells like K and L, they are having a highly energy difference, so they cannot share or they cannot mix to each other. But the orbitals that are present in a same orbit, that can mix or share with each other. So the L orbital, the orbitals of L will mix to each other. We can use a word mix to each other, or we can say share to each other. And how basically an orbital, if we talk about an orbital, it is having a 3 characters. Which 3 characters? First one is energy, means they possess energy. Second, shape. Shape can be spherical as well as dumbbell shape. Then third one is having electrons. These are the 3 characters of an orbital. So what will mix here? The question is that what will mix? So the energy and shape will mix to each other. Means they will mix. The energy and the shape of these orbitals will mix, but the electron will not mix with them. Why? Because electron have a negative charge. Electron have a negative charge. For example, if we talk about 2s2 or 2p, so here it is having a same electron and it is having a same electron. Same electron repel each other. When they repel each other, having a negative charge and having a negative charge, they repel each other, so they cannot mix with each other. So that is why electrons do not participate in the mixing or sharing. Only energy and shape mix together, they participated in mixing, and that mixing is known as hybridization. Here there are 3 elements: carbon, nitrogen and phosphorus. Carbon have 6 electrons, nitrogen have 7 electrons, phosphorus have 15 electrons. Now the question is that where hybridization the chances of hybridization is more. So carbon have 6 electrons, 2 and 4. Nitrogen have 7 electrons, 2 and 5. Phosphorus have 15 electrons, 2, 8 and 5. So in which the chances of hybridization is more? It will be in carbon, because it has a less energy difference. Here the orbitals will be having a less energy difference compared to the nitrogen and phosphorus, because it has a highly energy difference. Their shells are more than this, so that is why the carbon possess or having a chance of hybridization more than these nitrogen and phosphorus.